So look, actually, this is the first time I get to talk about this topic in a conference. So recognizing and with respect to a lot of the leading theoretical workers in this audience, I think my main job will be to try to carefully convey what we can or cannot say. And so apologies in advance for not really addressing that aspect. But implicitly, obviously, we need infinite theoretical help. So that's my general theme for the connection to the computational side. Already we've bothered lots of people. It's kind of remarkable to write this down in a short period of time. What I'd like to do is highlight some of the young people I've been working closely with. So in my lab, Denver, Kyuho, Bai, and Matoki have been leading the charge. Nobody slept for about 1.5 years, especially these three have other things that they're supposed to be doing. And so they're quite busy. Let me also take an opportunity to highlight Barrett Good. She's a graduate student of Lena Kupertis, partly because we've actually engaged very closely with her. And also I'll show some unpublished work that will be coming shortly. So she's gonna have some very interesting things coming up soon. Rather than list all the names, I should say that we've benefited a lot from X-ray scattering and spectroscopy led by Wei-Sheng Li at SLAC. Lots of theoretical interactions with people like Tom Devereaux's group on several occasions. Jan Zanen was on sabbatic last year, so he was around a lot, and also benefited for discussions and interactions with Sri Raghu and Rani Tamali. So this leads very little introduction in light particularly of yesterday's session. And it's a long-standing notion. That is to use analogies to the cuprates almost immediately, apparently after cuprates were discovered, people were starting to ask what other related systems might be available with that paradigm. And so I won't go through all of this in detail, but just to refer you mentally that there is a dome of superconductivity. It's proximate to an antiferromagnetic mod insulator, and the endpoint in the overdope regime is commonly understood to be a Fermi-liquid metallic endpoint. And the common structural feature, of course, is the copper oxide planes that in the hundreds of different structural manifestations is a common unit. Okay, so, and again, this is very much tying in then to yesterday's discussion. So the basic question here is to look for nickelate analogies. And with a view towards focus and brevity, let me explicitly say I'm already neglecting to introduce other nickelate-related activities I think many of you have been involved in. So the 214 nickelates, starting with the D8 electronic configuration. So a situation with strong electron-phonon coupling and stripe instability. In the last decade or so, there's been a lot of work on artificial heterostructures and quantum wells with D7 phosphate nickelate. Again, lots of activity here. And bilayer and trilayer versions of the structure I'm going to talk about. So let me just specifically narrow the discussion to the so-called infinite layer compound. And the basic idea is that looking at nickel next to copper, if I went from copper 2+ to nickel 1+, then the question is, can you make something that looks like the parent compound for cuprate superconductivity? Okay, so this is kind of a picture of the system I'll be talking about. And in a formal sense, indeed, it will share a D9 electronic configuration. And as far as I understand, these notions were kind of in the air even long before this, but the two first explicit papers thinking about this in terms of electronic structure is this one by Anisimov and then Lee and Pickett. So both of these were electronic structure studies, and you can already see one Pickett's opinion here. The title declares that nickel 1+ is not copper 2+. And indeed, I think this is quite a prescient paper. And I take here the LDA band structure that he calculates. And in the last 6 months, there's been many more, but at least in the LDA limit, I think there's strong consensus that the electronic structure is primarily a large hole-like, cuprate-like Fermi surface, dx² minus y² character, and 2 electron pockets. There's another one hidden behind this here that arises from hybridization with the rare 5D states and the nickel group. And so there's a little bit more heterogeneity as far as I understand in what happens, say, in LDA plus U or various attempts to deal with correlations. But qualitatively, again, the kind of consensus notion is this x squared minus y squared band will gap out into an upper and lower Hubbard band. And what's left then, to varying degrees, is an electron pocket, again, of this hybrid character. So experimental side, you know, the buzzword would be, this is a fun situation because we're taking kind of techniques of so-called soft chemistry and marrying it with thin film heterostructure. And so this is a little bit of a loose phrase, but broadly speaking, it's a class of low temperature chemical reactions that have been developed over the last few decades by chemistry people. You saw my youngest eating all the snacks on the Sunday reception. So this is just actually a reasonably germane and relevant picture of this. So you play the screen, and if you imagine chemical processes where you can de-interpolate specific sites, you can well imagine that you'll create a class of structures that are not thermodynamically stable, but can be metastably approached in rather unusual ways. Yeah. And specifically for the case of the nicolates, these are the three kind of key steps on which we build our work. The first one was to take powdered samples of lanthanum nicolate, expose it to hydrogen gas, and ultimately what is found is that there's a series of deintercalation transitions. You can sometimes stop in an intermediate so-called brown norite phase where we've slid this layer or this row of oxygen out. And then if you get the other one, then you're left with this infinite layer structure. Now, between 1983 and 99, there was quite a bit of controversy and debate whether this is real. It was very hard to reproduce. And so the next key step, again in bulk, was to use metal hydrides, things like calcium hydride by this group at Liverpool. And what they did was intimately mix calcium hydride with their phosphate powders. It was real chemistry, right? They're dissolving things, filter paper, that kind of business. This is really gave a firm foundation for the bulk powder synthesis and study of this material. And then about a decade later, another key step that we utilize is a group of Professor Shimakawa in Kyoto University found that you could actually do the same chemical processing in thin films. Okay? And so there are, of course, other very important papers, but these are the three key steps that we utilize. So soft chemistry is very new to us, but just in a flash, you know, what we're supposed to know how to do is make atomic scale heterostructures. In the last few decades, we've seen big advances in the ability to grow, not just by pulse laser deposition, but molecular beam epitaxy, off-axis sputtering, fairly precise structures where you can get towards single atomic scale variations in some fairly complicated heterostructure assembly. And another kind of growing theme has been to use heterostructures to approach metastable states in terms of crystalline phases or interfaces that are very difficult to access in bulk. And so we're going to merge these two together, and I think sometimes hard to visualize. I just wanted a picture of, we have this rather expensive and elaborate MBE or UHD chamber. And so this is the most important step. You're looking at a glass tube. This is a 2.5 by 5 millimeter piece, slice of our thin film, loosely wrapped in aluminum foil. These little rocks are calcium hydride. And so we vacuum seal the whole guy and anneal it at fairly low temperatures to induce this oxygen deintercalation reaction. So this $5 experiment is actually quite hard. So let me show you some of the people that were doing this. So as I said, there was some small but established body of work on this, and we got it to work pretty well, but we could never dose them. And so this actually has a long history. So Hwang was a postdoc with me and made these initial steps, and we tried everything: ionic liquid dating, fine control of the oxygen storing geometry, but we could never really get it to work. I should say she's doing well, so you know it wasn't career ending, but it was quite frustrating. But at least for the undoped nicolates that that had been studied, somehow there was very little work on the electronic structure. And so the first of a series of very important accidents, so good fortune, was that we started to work with Lee, who was interested in using XAS and RIX to study this system. And the typical laboratory thing happened. He left. This started to get interesting. We needed a few more samples. And then Lee had just joined later that year and was working on perovskite nickelate membranes. So membranes are another kind of activity in the group. And he kind of jumped in to make additional samples, and we revisited this notion of doping. So another kind of a lucky accident motivated this idea, which was we had tried to make the infinite layer structure and then subsequently dope it. And I don't say it can't work, but we couldn't do it. So the idea was, why don't we substitutionally dope the perovskite phase and then do this reduction chemistry? And it accidentally happened that years ago, as a summer intern, at one point, I a little bit played with doping, ironically, the exact same perovskite nickelate. Right? So this is part of the way towards the superconducting compound after reduction. This is quite an interesting system. Of course, many of you know, it's a paramagnetic metal and a strongly first order phase transition to the kind of canonical, charge, spin, orbital ordered configuration that we all like. And what was interesting was that fairly slight doping could drastically move this around, and actually by 5 to 7% strontium doping, you can completely suppress this. So that was the idea, and this was a first scan using the lanthanum version of the nickelate. So this is now the reduced form. And you can kind of see what's happening here. So a nominal different strontium doping levels, and you can see that this guy gets fairly low. So resistivities of a few million centimeters, it looks like it's close to becoming metallic and interesting, but not quite there. I should say that now, looking back, 2 years ago or whatever, we know a lot more about synthesis, so this is worth revisiting. But anyway, motivated by this, the idea was it smells like it's very close to becoming metallic, and it makes the system a little bit have larger electronic bandwidth, and so go to something like rubidium with a smaller ionic radius. So that was the idea. But I can also say very honestly, I strongly recollect saying we had spent the better part of 4 years trying this, so we should really stop doing this. But luckily, Denver ignored this, and this was kind of the first partial superconducting trace. So just to be clear, this is far from zero, so this is down to 2 Kelvin. But the first taste that something interesting might be happening. And actually, our first paper on this was submitted more than 8 months later, so you may ask kind of what took so long. And I should say this is kind of the most challenging materials issue that we've ever been, or I've been involved in. And so in words, I could say that the following. So nickelates want to be most stably like nickel oxide, nickel 2+, and nickel 3+ is a secondary oxidation state. So what we're trying to do is rather to go to a very high, unusually high oxidation state of nickel in this doped perovskite form, and then go to something unusually low. Now we want to use epitaxial stabilization, as we'll show you it's quite integral. But this transformation changes the lattice by 3%. So, it's quite a, a complicated and rather fascinating system, I would say. So to just give you an idea how the starting point was, so this is a cross-sectional of that kind of a sample at the early days. You need to have loving eyes, but it turns out this first 1 or 2 nanometers was this infinite layer phase that we will eventually argue is the superconducting phase. You can see it's a mess. It's segregated, it's falling apart, all sorts of crazy things that happen. And so after a bit of work, maybe I should speak over here, but got to the case that we could stabilize a few nanometers thick of this infinite layer phase. You can kind of see that by the Fourier transform. This elongation in the Fourier transform is indicating that we've compressed the C-axis by deinterpolating the oxygen. So this kind of sample does show a complete zero in resistance, but still, you know, who's to say what of all of this is superconducting, right? But one thing that you can see in our own work, this is not our discovery, at least in the undoped case, people had already seen that actually this Superconducting transformation for film seems to nucleate or stabilize very well up against the substrate. So we're in conditions where the structure tightening substrate is invented first. And you can see here the details vary from group to group, but you can see a few nanometers of the internet AFAs, less visible here, and the complicated zoology of decomposition and things on top. And so the final step in this initial foray was then to say, if that's kind of giving you a stabilizing proximity effect, let's do it from either side. And so here you can see a reasonable early sample where we have now packed this perovskite nickelate with a layer of strength and tightening. And I'll come back to a more detailed discussion in a moment, but we can see that indeed it's normally this infinite layer phase throughout. And as I'll show you, we've made some improvements, but right now our approach is still has this kind of thickness limit, meaning our best, whatever uniform single crystal thin films are limited by about 10 nanometers. So that's our current situation. So, you know, the better part of 7 months got us to here, and now finally we're like, okay, you know, we understand or believe that we have a which phase identified associated with superconductivity. So this is as of last summer. Let's say this got to us through let's say a reproducibly complete transition. You can see there's quite a bit of scatter here. I won't talk through the details, but let me show you then kind of detailed examination quickly of one of these reasonably well-formed samples. Again, kind of mid last year. So here's an artist rendering of this de-interpolation transition that left off the top structured technique cap. And now by things like I said, it looks quite nice. This is the perovskite phase. We have the O1 or O2 diffraction peak. By de-interpolation, they shift off to the right. And essentially, all markers are pretty good. The thickness is corresponding to the thickness limit of the film itself. You can see different fringes. And in all the cases I'll describe, our films are always epitaxially clamped to the lattice, the in-plane lattice constant. So to talk through what we find, so let's first look at the perovskite version. So this is the undoped ruthenium nickelate perovskite. This is again this famous first order phase transition for this V7 electronic configuration. And by doping, it looks metallic all the way down. And by now taking one of the oxygen out in these planes, we go to anomaly D9 configuration, where in the undoped case you have this weak upturn at low temperatures, and in the doped case we see a superconducting transition. So to give you the basic superconducting properties, the critical current here, let's say the narrow bridge of this guy is at that point pushing 200 kiloamps per centimeter squared. I should say now we're up to 350 or 400. And so it's indirect, but one of the ways that we felt convinced it has to be kind of attributed to, say, the uniform film rather than an interface is this would require many orders of magnitude higher critical current density than, say, seen in 2D systems like DMDs or bilayer graphene or interface versions of this. If we look at the magneto resistance of this transition, you can take off an estimate of the superconducting coherence length. We get something like 3 to 4 nanometers typically. And this is just neglecting details of broadening of work. This is kind of a ballpark number. And finally, with a dual coil mutual inductance measurement, you can see the superconducting transition and associated tuning. And again, at this early stage, it's very difficult to say quantitative things, but let's say, given a range of possibilities for the order parameter symmetry or the scale and effective disorder, in any case, we would get a few microns. So that's kind of the scale of the London penetration depth. So extreme type 2 in that regard. So a few questions, of course, the central question that motivated a lot of this thinking was to what extent D9 nickel is the same as D9 copper. Yeah, I don't need to say more about this to this audience. Right, okay. Somehow I went slowly. Okay, so the first statement is that previous bulk powder studies showed no evidence for magnetic ordering for the unbuilt parent compound. And let me summarize the work of Matthias and Lecheng just here. The summary statement is by spectroscopy, what we find is that rather than the charge transfer-like landscape you see in Q plates, we're a rather different here, and more in the Mach-Hubbard regime, which is rather unusual considering where we are on the PF table. So of course, doping into holes into the system leads to this famous Young-like singlet. The statement here is that although there's a remnant of this dehydration, there's also apparently another electronic band derived from, again, excluding by dehydration. And so the notion is we're very far up here away from the oxygen PP band, and so the structure and the nature of the sequence is rather different from the Q plates. So the experiments underlying this picture I'll maybe not walk through in the interest of time, but you know, comparing nickel oxide, a canonical transfer insulator, and a frostite D7 version of this nickelate. Correspondingly, again, we're in a very different regime here. It's rather unusual, and I think you can easily attribute to the very low oxidation state. And speaking specifically of this, singlet issue, you can see here this oxygen feature that's prominent in nickel oxide or the nickelate, the frostite, is vanishingly small for the infinite layer phase. So cool. Working very hard to improve the crystallinity, and so I wanted to give you a kind of a representative state-of-the-art sample. So again, we're limited to about 10 nanometers. You can see if you look over here, it looks pretty nice actually. So in some ways, we're rather proud of this. Right? But also, to be fair, there's a fairly high density of extended defects. So here's this rectangle here, the nail down here, and you can kind of sort through. I'll skip the details that you can find in a recent thing we put on the archive, but essentially these look like defects that are based on vertical Rodelson copper type extended defect faults. And the upshot of that statement is that whereas bulk sensitive measurements like lattice parameters and nowadays TC and the Hall coefficient are quite reproducible at a level I'll show you, the magnitude of the resistivity is still bouncing around a bit. Okay? And we speculate or attribute it to the details of the density and distribution of these extended defects. And so what I'm going to show you now is properties associated with the doping series, but this is kind of the landscape as far as we see, and not much changing systematically with doping. In any case, here's kind of a first statement I think we can make now about the doping dependence of the system. So if we look at the C-axis lattice parameter, these aren't error bars, but this is like 3 to 5 samples, and these are the extremal values for a given one with respect to the average. So with this kind of a spread, it's pretty well reproducible, monotonically varying, qualitatively similar to the P plates, with the caveat that it's about 3 to 5 times larger. And this notion that there's a higher sensitivity to raricite, not in the presence of doping, but very rare radius has been seen in work of Tom's student under which you can find as well. Okay. So doping dependence of transport. So first we could just talk through about the representative samples. So it's rather strange. The cuprates, you go through many orders of magnitude as you go forward into the mod insulator. Here's x equals 0. It goes down and back up, but the whole variation is fairly narrow in the vicinity. Representative, again, modulo this variation. I showed you here, hopefully. Okay, so this one's been done in the literature before, but 3 samples for each of these guys, and the color one is the one we use here. So hopefully, some of them you can't see, there's a second one too. We just kind of took a middle typical one. Qualitatively, the temperature dependence is reasonably close to one another, and it's again as if we have a series resistance that you have to consider in terms of these defects. If you look at the Hall coefficient as a function of this doping series, it varies quite smoothly. I'm almost done with it. Yeah, the simple statement would be if I take the undope guy at room temperature, it'd be something like 8% electron dope. We normally put strontium in, and it's as if we had more and more electrons. So it's very non-physical. We have smooth crosses of 0 both in temperature and density by doping. And so the simplest qualitative picture you can imagine that nicely explains all of this is a situation where you have electron and hole-like pockets. I'll skip the details and just say this is qualitatively quite nice. You can't pull out real numbers, unfortunately, because it's linear up to 14 Tesla, so that's why. And so this is highly under-constrained, but qualitatively, I think, in the right direction. Okay, cool. So let me just say this, and then I'll just flash my summary slide. So this is the phase diagram. This is down to base temperature of dill fridge. So, let's say down to 30 millikelvin conservatively, a superconducting dome that looks like this, and just contrast it with the cuprates. Maybe with the last gas discussion, I think this is both interesting and shows you the issues that we face. So this is a resistivity of 20 Kelvin right above the superconducting transition. And this is for all the samples, and you can see that despite the scatter, the overall trend is very clear. That the superconducting dome is associated with a minimum of resistivity, and at a very hand-wavy level, this would be kind of a border of the off-the-regular limit, right around here. But what's quite different from the cuprate is we neither go to a good insulator on this side or a good metal on that side. And maybe I should stop, but happy to discuss that a little bit more. And the summary notion would be many of many of you, are thinking that understanding superconductivity in the cuprates requires an understanding of the normal state. And so this comparison is rather interesting, I think, in the context of that program. So I'll just stop there and thank you for your time.
Okay, great. Thanks for a fascinating talk. And we have time for a couple of questions. Just we'll remember to repeat them for the Zoom.
Okay, sure. Okay, the question was what is the pairing symmetry? And the simple answer and the hard answer is I don't know, and I don't know. I don't mean to be dismissive, but we don't have any experimental statement we can make. So we are eventually interested with further materials control to do bilayer type of experiments. We're interested in studying the mutual inductance and the superfluid density, but we don't have any experimental statement at this point. A single band cartoon estimate of KFL equal 1. Yeah. So
repeat the question.
The question was in the normal state right above superconductivity, the superconducting samples are all of order the off-the-regular limit, and I said yes modulo a simple Boltzmann estimate for KFL of order 1.
There was a question about
the question was, should we view these as quasi 2D? They certainly have a 2D crystal. Okay, so that's not a useful answer. We would love to start probing the C-axis conductivity in any form. What is different here is that this electron-like pocket is quite a three-dimensional like object. This is from Tom's group's Vanier kind of projections. So that aspect should be rather different from the cube rates. But we don't yet have an experimental probe, let's say, of the C-axis response.
Okay, Gabi?
Is there anything known about the magnetic stability and magnetic properties of these type of compounds?
Okay, again, is anything known about the magnetic susceptibility and magnetic properties of this class of compound?
So A, not reliably for our films because we're dominated by the substrate. Bulk powder work is very difficult because even in the best work, I mean, it was very brilliant work in Liverpool, there's a few percent secondary phase, which tends to be magnetic. And certainly that's the agenda of my colleagues like Wei Sheng to use RICs to go after looking at magnetic excitations, but you know, to be done.
Okay, last quick question.
Yeah.
Why do you think it's not related? This doesn't seem like bottom as well.
Yeah, so the
Okay,
question,
so okay, go ahead.
yeah, the question was why you need a capping layer, and the issue was, well, that after a few nanometers, there's kind of a decomposition reaction above that, and so this is kind of a mess. I mean, now we know that it's fairly low conductivity, and we can kind of separate this out. But the thing of a capping layer is then it normally allows us to be single crystal all the way through the thickness of the film. And so we kind of know what we're studying. And so that's still our preferred mode for things like resistivity or transport in more detail.
Okay, great. Thanks. That's lots of great discussion. We'll continue later on.